Alright, I think I have most people in here that are gonna come up. No, sadly, Beer's Law does not refer to stouts and IPAs. Beer's Law is a relationship of absorbance to concentration, which is what we're going to start talking about, because the lab for this class that I didn't get to talk about on Monday is actually a little involved, so we're going to start there. Before we do that, though, welcome back to Chem 161. Man, have I had a week. Man, have you guys had a week. So you had your exam, and then Canvas screwed up all of my exam grades, which I'm just finding out about. So some students' exams just showed up as, oh, they didn't take the exam, and then I go look, and there's a score there, and it just wasn't carried over. So I'm going through all the scores that everybody has turned in for everything in all my classes manually, and it is very slow and tedious, and I haven't gotten to 161 yet. I just finished 140, and found 2 errors out of 400 so far. But because there were 2 errors, I can't trust the gradebook anymore. So now I have to manually check everyone's grade. So I'm doing that. I will finish that after class tonight. It takes me like 30 minutes to do all your entries. I throw it in Excel and I just prepare a formula, and it's just, can I copy numbers? And it takes time. And if that wasn't enough, I had a back spasm yesterday, which is why I missed my lecture. I couldn't get out of bed, and I had to have somebody come over and help me get to a clinic so I could see a doctor. And it's one of the joys of getting old, I guess. I don't know. So I had to cancel all my classes because I had no idea how long I would be at the doctor. And I left at like 8 a.m. and I got back at like 2:30. So I probably could have gotten away with just having this lecture, but instead I opted to go to sleep because I didn't get any sleep the previous day. And so even 2 or 3 hours would help. Yeah, it's not great. I'm still not super great right now. I might be due for another, what is it? Naproxen here in a bit. I'm basically, like, every minute or two, I start rolling my shoulders, kind of like I am flapping my wings as if I were a chicken, to just try and, like, massage them, because I can't reach my back. Like, who can do that? And there's not really much that I can do about it, other than, not be sitting, but unfortunately I can't stand and do this because I have to write on a tablet, which is at like waist height, and I can't do that. So I'm just sort of dealing with it. So if I start to sound kind of like I'm moving, or I'm antsy, or I can't focus, one, it's because I'm doing something else, like I'm trying to roll my shoulders so that they don't hurt all the time. And 2, it's probably the pain meds. Like, I'm on a painkiller right now, so. Alright, so let's talk about the lab. We're not going to talk about this just yet. I need to capture... Oops, I don't even have it open. Where the heck is it? There it is. Okay, so let me put this on the screen here. Don't worry about the slides just yet. We're going to come back to that. But I appreciate everyone's concern. There's nothing I hate more than canceling class. Whereas, as a student, I imagine there's nothing that you guys enjoy more than me canceling class. Let me do this instead. Like, yay, we don't have to go to class today. Woo! Have I tried yoga? I would love to do yoga if I did not have to leave my apartment to probably do it reliably, because I won't do it here. Like, I have too many distractions. Yeah, I don't know if this is a pinched nerve. I feel like it's more like a, like I sat at my chair funny. I remember one day I adjusted my chair to, like, tilt it back a little bit. And then that night, like, I was like, oh, whatever I did was not good. That was a mistake. And my back has been kind of bad like that for the last week and a half. I've definitely done the leg thing. I rode my Harley over a bump in the road, and my suspension is just shot on my bike because it's like 10 years old. So I basically jackhammered my spine once, and after that I've had sciatic issues on occasion, like I will bump or twist or do something, and then my left leg or my right leg will have just shooting pains down it for like 4 months, and it just comes and goes, and it's just like, ugh. The joys of getting old. Anyway, let me put that on the screen. Hopefully you can still see this. You can see it if I scroll it. I can't actually see the thing here. Yeah, there we go. Now I can't see the chat, so let me just move this over for me. All right, so what we're going to talk about is Beer's Law. Beer's Law is an interesting phenomenon that has a very simple relationship to it. So you can read through all the theory here on your own. So the theory is that light transmits through a detector. Actually, you know what we'll do? Let's go to this window. And this is going to have to get resized again, but that's okay. Okay, so now I can do that. And I can draw all over the screen here. So the theory is that if you have a sample, like, say, this, and I'm just going to make it blue for whatever reason, and I shine light through the sample at a detector, some of that light is going to get absorbed by the particles in the solution. So, like, there's stuff in here. And when that light is absorbed by it, it will then be irradiated out in all directions. So the amount of light that I initially transmit, or I guess I should say the amount of incident light that passes through, and the amount of light that gets to the detector are not going to be the same. Some percentage is going to make it through, and the other percentage will be absorbed and then scattered in random directions so that you can see it. Otherwise, it would just be a black void, right? If no light was emitted from it, you wouldn't be able to see it because no information would reach your eye. So we call this transmittance. So transmittance is the ratio of how much light goes through to how much light you were intending to send. And so this will be some percentage. So like if half the light went through, transmittance would be +5. Or 0.5, sorry. Then what we do is we say, okay, well, this number isn't super useful to us. We're going to just make this new number. And this new number is called absorbance. And absorbance is just simply minus logarithm of whatever you put in for t. And that formula is in here somewhere. There it is, right there on the screen. And the reason that we care about this formula and not transmittance is because an interesting phenomenon occurs when we plot absorbance versus concentration of solution. And that pattern is this. It sort of goes like this. And you might think that's not really a useful pattern, but if I say stop here and I look at just this region right here, then the shape that I've enclosed in here is basically a line, right? So if my absorbance doesn't exceed about this much, then what we can do is we can trust that the relationship between absorbance and concentration is linear. Or in other words, the absorbance of a solution is some constant times its concentration. Now, we're going to define the slope of this into two terms. So the first term is going to be this. This is called the molar absorptivity coefficient. And what this number represents is how much light does the solution absorb. Like, some solutions are so intensely colored that if you put a little bit of dye in them, it gets super, super dark. So, like food coloring, if you put 1 drop of food coloring in there, in your solution, it gets intensely dark. Like, red food coloring is very concentrated, and it's very good at absorbing light. But if you do the same thing with yellow, you could see through yellow no matter how much you put in there. It's hard to make a yellow solution of food coloring be very opaque. So the difference between those is that the red ink or blue ink or whatever that's very dark and very opaque absorbs more light than the yellow one would. So the red ink would have a higher molar absorptivity coefficient. Now the units of this are going to be liters per, that's a really long L. Wow, okay. So liters per mole times centimeters. And you'll see why these units are like this in just a second. So this is not the only thing that's in X. So this is part of X, but there's another thing too. And that is this. This is also an X, and this is called the length, or path length. And path length is just simply how far does light go? Or how wide is the sample? And that's going to be measured in centimeters. Typically speaking, our path length for our devices that we're going to use is going to be fixed to as close to 1 centimeter as we can. It's standardized. And so what ends up happening is that the relationship for this line right here becomes this. Absorbance is equal to the molar absorptivity coefficient times the path length times the concentration. And this is called Beer's law, or the Beer-Lambert law. So in other words, absorbance is just some trait that we've made up because when we look at it compared to concentration, it makes a line. Transmittance doesn't. It makes a sort of logarithmic curve, which is why we don't really care about transmittance. But transmittance is used to calculate absorbance. So transmittance is just the ratio. If we go back here, if I can click on the bar, there we go. Transmittance, which is T, is just the ratio of how much light makes it through to how much light we intended to send through. And then when I take the negative log of that, I get absorbance. All right, so what this means is that you're going to plot different concentrations of solutions and then plot their absorbance on the y coordinate. And you're going to get data that looks kind of like this. Doot, 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 doot. And it'll make a line. Then you'll tell Excel, oh, I want to make you, sorry, not Excel, the Google Sheet. Tell it, oh, give me a best fit equation. And once you know that, then you can say, okay, if this is my absorbance for my unknown, this must be my concentration, and calculate the concentration of unknown solutions. And that's basically it. That's all that we're doing for this lab. So when you go to the lab worksheet and you look through this, I believe there's a video in here that shows you how this process works. Yeah, here's the video right here. And what the video will do is they will show you the entire procedure, where you make a solution, you put it in the detector, and then it plots the data on a graph, and how you get that data onto the graph for you. Because normally you'd be plotting this on the computer, and it would spit something out that just looks like this for you. Instead, we're going to have you manually collect the data, which I've done here, and you're going to make your own chart. Now, we've already covered how to make a chart. We did that in the first lab when we talked about the sugar solutions. You're going to follow the exact same procedure to make the chart. Now, the other things that we want to talk about in this experiment, just really briefly, there's a color wheel up here. There it is. The color wheel shows how light that is absorbed is visualized. And the way that this works is that when you shine a beam of light through, one color will be absorbed more than the others. The color that's absorbed, the opposite is what you see. So this color wheel shows you the opposite color. So if I were to absorb blue light, do I have a cursor here? Yeah. So if I was to absorb blue light right here, the color of the solution would instead be orange, because orange and blue are opposite colors. They're complementary. Same thing over here. If my solution absorbs yellow, it appears purple. You just go straight across the color wheel. And this is true for all things. If you shine white light on something and you subtract out one color, the color you observe is the opposite of the color that was absorbed. It's the complement to it. I can't think of anything else. You're going to have to make solutions. We talked about that in Unit 6. So you're going to make dilutions of these solutions right here. The concentration is shown right there. You're going to be using tartrazine. Tartrazine is a yellow solution. It is yellow number, I want to say yellow number 1, and it's basically the color of yellow Gatorade. That's tartrazine. And then you're going to answer some questions about it at the end. That's it. If you know what you are doing to make the graph, this won't take you more than an hour, presumably, to do. All right. Any questions, let me know. Give me just a sec. I'm going to get all of this set back up here. Okay, so I think that I have uncaptured what I wanted to, so we can go back to this. Okay. So yeah, let me know if you have any questions about that. Yeah, I honestly have forgotten what the video tells you to do because it has been so long since I wrote the lab and found that video. I'm sure it's relevant in some way because I wouldn't have put it in there if it wasn't. And if it just shows you how to use the program, then that's because I want you to see how the program looks, because at some point you will use Logger Pro again. Logger Pro is actually super useful. I'm not a big fan of software, especially software produced by learning and educational companies, because they're usually not produced by teachers. But Logger Pro is actually really, really good. You would use Logger Pro as a graduate student in a laboratory to do research. Like, it's very powerful. And I honestly wish I knew how to use it as well as I do now when I was a student, because I would just hooked up a laptop to everything I did and had all this data. All right, so let's talk about the Bohr model a little bit more. So when we... Actually, let's go back to here real quick. When we left off last time, we talked about the following phenomenon. And that was that if an atom has electron energy levels that are spaced apart from the nucleus, electrons will reside in those energy levels. And that there are an infinite number of them. And you can't see that because this needs to get cropped. There we go. Now my electrons, which I'm gonna start using electron symbology. This is an electron. We'll talk about why it's a pointy arrow later on. Instead of writing E every time, I'm going to write the actual symbology that's used for an electron, which is this pointed arrow with just a hook. So we don't use this symbol for a very specific reason that you'll encounter in organic chemistry. This indicates 2 electrons. This indicates 1 electron. All right, so I'm going to put my electron down. I'm just going to have it in its ground state, and that will probably be at the lowest energy level. Electrons have to go on energy levels, like we discussed before, because they are quantized energy. And that these numbers represent the sort of harmonics for the wave function that represents an electron. Remember that electrons, just like light, we were starting to get to the concept that electrons are both particles, but they also behave like waves. And these levels represent the different energy levels of those waves. And my electron could be at any of these that I want it to. But at the lowest possible energy, it'll be in the ground state, which is the lowest level available. Now what I'm going to do is I'm going to give it energy. So here's my energy. And my electron will now jump up somewhere, depending on how much energy I gave it. So I'm going to assume, I don't know, let's say that I went up here. My electron absorbed the energy, so it gained energy. So that would mean that this process right here is endothermic. The energy was absorbed by the electron. Then I could say that my electron will fall back down to any level below it. It does not necessarily have to be where it started. It could go anywhere it needs to. So I'm going to say it goes here instead. Now, when I lose energy, that process would be exothermic. The energy is coming out. And the energy transmitted is going to be related to the difference here, final minus initial. We're going to take the absolute value because this bottom number is going to be lower than the top number, although we haven't actually talked about why this is going to work out anyway in terms of numbering. But this is the general process, and this energy right here is the energy of the photon that you observe. Now, we related these energy levels to the Rydberg equation, which was this. So the wavelength that you observe is equal to some constant times and I always forget this because I don't use initial and final here. I just plug in the numbers so that it works out. So the smaller number, so this is going to be final, needs to go first because you want this smaller number will be a bigger fraction. And this is for electrons falling. From the initial energy to the final energy. And so we did an example of that last week. And we're actually going to have you start by doing another example of that today. Even though I tested you on it already. I want you to still do another example because it will show up on a quiz. All right. Okay, so this slide is just basically summarizing what I just said. All right. Now, very, very important, the Rydberg equation that I've shown you only works for hydrogen. So if I go back to this slide, you'll notice that the variable that I put there, RH, this H is for hydrogen. Every other atom has a different Rydberg constant. And it's modified by the number of protons that are in the nucleus. So what that means is that if you try and do this for helium, you get a different result. And the reason that you get a different result is because if you increase the number of protons in here, so this is what the diagram would look like for +1, but if I had 2+ down here, all the energy levels tend to do this. Whoop. They get closer to the nucleus. And as I add more protons, everything starts getting closer and closer and closer. So let's write that down. So maybe not in that color. So as more protons are added, so with more protons, energy levels fall closer to the nucleus. You can't see. Grumble, grumble, grumble. I hate everything, and I can't undo it. Yeah, you can't see what I'm writing because I didn't click the damn thing. Okay, and I can't undo. So what I'll do is we'll just draw it again. Alright, so here's my nucleus. And let's suppose that I only have one proton in the middle. So I'll just do this. Alright, if I increase the number of protons in the nucleus, any electrons that are out here are going to be pulled towards it with more force, which means that all of these energy levels will then slide like, oops, like this. Whoop. So the end result that we observe is that as the number of protons increases, each energy level changes its distance from the nucleus. Now, universally, all of these tend to get closer. But they don't get closer in the same amount. And so what that means is that n equals 1 is the closest to the nucleus, so it'll get pulled the most. But n equals 5 will only get pulled a little bit. So as everything starts to get closer to the nucleus, all of these energy levels tend to spread out and have different distances between them all. And the result is that you get different colors for different transitions. And if we go back to this slide where we saw that, there we go. You can see the different transitions that aren't the same colors at all. For hydrogen, we have very fixed lines which represent the transitions between each different level. And if I go back to this diagram right here, you can see that this kind of looks like this diagram right here, doesn't it? I got one that's kind of far apart, then another, and then they start getting really close together. And there's that right there. But with helium and barium, there's just all the lines get stretched out a little bit more. So you could see that kind of starting to happen here. But then why are there all these lines over here? And the reason for that is all of our transitions just kind of have been scrambled, essentially. So different elements that aren't hydrogen are going to have different line spectra. And that's because when you add more protons, all these energy levels shift around. So don't think that n equals 1 and n equals 2 and whatever are all just fixed at some distance from the nucleus. For our discussions when we're talking about hydrogen, they will be, because we're going to be referring to hydrogen every time. But when we talk about other atoms, those energy levels will slowly start to scoot down towards the nucleus. And thus we're going to get a bunch of different spreads for energy. This is going to be relevant for you in lab number 4, where you're going to actually calculate all the possible transitions for hydrogen using Google Sheets. You're going to do 100 Rydberg equation calculations. But the point of the lab isn't to do the Rydberg equation. The point is to learn how to do calculations automatically in Excel. You program the formula once, and then you just drag it everywhere, and it'll do it 100 times. All right. So enough about the theory behind the Rydberg equation. Let's actually have you do the calculation. Okay. So again, we're only going to focus on hydrogen for this class. If you look up the Rydberg equation on, like, say, Wikipedia, you're going to see this in there. Z is the atomic number, and that just modifies the equation based on what element you're using. And then there's a further caveat. We can only solve for a system with one electron, because electron-electron repulsion ruins all of our calculations. We can only work with species that have one electron in them. So we're limited to hydrogen and hydrogen gas with one electron, so H2 plus, or helium plus. Anything else is just, it's too charged. We get kind of weird results. So we're going to stick with hydrogen. When you get to 300 level chemistry, we'll give you dihydrogen with one electron in it. So you can do it that way. But yeah. All right. For our example, we did this calculation. We did n equals 3 to 2. We found that it was this line right here. I want you to use the Rydberg equation to tell me the wavelength. Give me a wavelength in nanometers for the transition from 4 to 2. And tell me which line it corresponds to based on the number you get and what color that represents. Now, there might be extra transitions in here, so don't automatically assume it's the next one. But I want you to calculate the wavelength and tell me which line shown best approximates that wavelength. So go ahead and do that calculation. If you need the Rydberg equation, it's in the slides back a few pages. So you can reference it there. And we'll go over the answer in about 5 minutes. So see you in a bit. Actually, I'll just write the Rydberg equation on the screen here for you. That's not the version I want. And then RH. Oh, 1067. I think this is right. I'm going to look that up, but give me a sec. I was real close. I forgot a 9 in here. Boop. So we're just going to edit that. There you go. That's the Rydberg constant. I have most of these memorized not because they're important. The Rydberg constant is probably the least important because I do this so often. Don't memorize constants. Nobody's impressed. It makes you look like a nerd. Like, nobody out there is watching this and going, wow, that's impressive that he knows this number. Like, nobody cares, right? Okay, go ahead and solve the equation. Sorry, if it looks like the chat is moving, it's because I realized part of it was cut off. So now we can all see everything. When you get the answer, type in your wavelength or just your color. If you don't know, just guess a color. Say purple or cyan or blue. Or say red. You probably shouldn't say red. All right, we ready for the answer here? All right. So n equals 4 to n equals 2. We don't really need this anymore. I'm going to draw that diagram like 75,000 more times in this chapter, so I really should just find one and copy and paste it and have it just handy. I'm writing the wrong version of this equation. There are two versions of this equation. And I'm used to the one that uses energy and you'd go HCRH, but that's okay. Let's see here. So I want to solve for n equals 4 to n equals 2. So I'm going to solve for 1 over lambda first, and then I'm just going to take the inverse. So we got RH times 1 over n final, so it's going to fall down to 2. And it's going to fall from 4. Now, our n levels are exact. Those are all integers. So let's see here. 2 to the negative 2 minus 4 to the negative 2. Now, just in case you didn't know this, if you want, you can type this equation in like that. Because remember that the inverse of something is just 1 divided by that something, right? And so this would be the same as me writing this, because you could just multiply the exponents, right? So if you're trying to punch this in your calculator and you don't want to use parentheses anymore, just type this. You should get 1 over 4, right? Which is 0.25. And so you could check that really quickly that you're doing it right. So for this part, I got 0.1875. And that's an exact number because these were exact numbers. And I'm going to multiply it by the Rydberg constant. And I get, as my answer, 205,645 455. That should have 7, right? Yeah. And that's inverse meters. So now I'm going to take the inverse of everything. And so that's lambda equals 1 divided by this number. And I get 486.2737 meters. Oh, hold on, sorry. That's nanometers. I got 4.862737 times 10 to the minus 7 meters, which I then converted to nanometers because I'm cheating, basically. Now, which color is that on the scale here? So if I go over here, and I say, okay, well, this is 700, and this is 400, so midway between them would be about 550. And midway between those should be 475. And the answer that I just got was 486, so this must be 486. And that makes sense, right? Because if we're looking at hydrogen and the orbitals aren't really changing much, if this is 3 to 2, then this must be 4 to 2. And then this would be 5 to 2. This would be 6 to 2. And then this one's 7 to 2. Now, that's not always going to be a safe assumption, especially not for other elements. But for this one in particular, it turns out it does work. All right, what do we got? Oh, it's break time. Yeah. All right, so I'm going to give a 10-minute break. I actually have to get up and walk around because doctor's orders. When we get back, crazy shit. See you then. That's the wrong card. That would have been a much more poignant transition if I had actually hit the right button. Anyway, more Mega Man. I need just a second to reply to an email, so hang out for a bit. Alright, sorry about that. Let me wind down Dr. Wiley here. I had a bunch of emails from students. They're like, I don't see my score. What's going on? And I'm like, yeah, I know Canvas is the worst. Because Canvas. So, okay. So I need this out of the way. Okay. Aside from one particular problem that I don't really care about, I don't remember if there's a quiz question on it. You know what? Let me just look that up. I do not give a shit about de Broglie wavelength. But there might be a question about it, so I should probably look and see. So give me a second. I'm looking through the quiz bank. Light, nodes and waves, Rydberg, miscellaneous, XO, shapes. I don't see one. Okay, cool. Yeah, throw your calculator away. Don't actually do that, but you no longer need a calculator for this class. Congratulations, we're done with math. I don't know, what's an appropriate sound effect to play for we're done with math? Let's see here. I don't know. No more math! Hooray! Yay! It's all concepts! Sure, we'll just whip out the Smash Brothers for that. Alright, no more math. That's it. We're just going to talk about stuff. We're going to abstract math from now on. There's music playing, and I don't know why. Oh, because it just went to the next track in the playlist. Okay. What we're going to do from now on is we're going to abstract math. What that means is I'm going to show you an equation, and I'm going to do something like this. If this number gets bigger, what happens to this number? Well, since I'm multiplying them, this would get bigger too. That's it. That's what we're going to do. Now, that's not to say that the math won't be important, because we're going to introduce you to an equation called Coulomb's law, which is going to look like all sorts of crazy numbers and variables and whatever. And I'm going to cross out like half of them because we don't give a shit. So we're not going to give up on math concepts, but we're not going to calculate anything. We're not going to deal with units anymore. You will still have to do that in the lab, unfortunately. But as far as lecture is concerned, we're done with numbers. Sort of. We're done with calculations of numbers, I should say. All right. So let's talk about how things behave in the physical universe. Yay. What you're used to is called classical mechanics. Classical mechanics follow Newton's laws of motion. And these are the equations that work and energy describe. So this is like you throw a ball. You can model how the ball will move by using 1/2 mv squared for its kinetic energy, by using parametric equations to model its vertical and horizontal displacement due to gravity and velocity. All sorts of stuff that you've probably done in a basic physics class before. Tinier objects do not follow classical mechanics because they experience forces from all directions, and they themselves exhibit those forces too. They follow what is known as quantum mechanics. Quantum mechanics is basically the result of, these objects behave like particles, but also waves, because waves represent really, really, really tiny things that have zero mass. These things are so tiny that their behavior is influenced by things other than their mass. So this would be like charge. Two electrons get together. If you throw an electron past another electron, it does not behave classically. It would not move in an arc. It would move in a very chaotic pattern. The takeaway is that quantum mechanics does not behave like classical mechanics does. There are issues that we have to address. And so we're going to talk about those issues first by discussing a little bit more detail about things that waves do. Now, we mentioned earlier that if I had photons of light, and those photons of light had the same frequency and wavelength, I could line them up in such a way that I could increase their amplitude. So this would be like one photon adding with one photon, making two photons. If that was supposed to be an S. If they were both waves, the wave would just get bigger. You could mimic this sort of behavior in a bathtub, or by holding onto a slinky with somebody holding the other end. And if you do the waves just right, they will get bigger and bigger and bigger because the energy you're imparting will sum into the wave as it comes forward. Now you can do the opposite. You could actually wave the slinky in the opposite direction so that you wave it down when the previous pulse is coming back at you in the up direction. If you do that, they would sum to 0. If you had two photons that had wavelengths that were offset by exactly lambda over 2 meters, where lambda is the current wavelength of the photon you're looking at, they would destructively interfere and they would sum to 0 and you would see nothing. The total energy of their sum would be 0. So these phenomenon exist. Constructive interference and destructive interference. These both exist. Now, how do we know that they exist for things like matter? Like, this doesn't really make much sense that electrons would cancel each other. They don't really cancel each other, but their observational properties can be canceled. We're going to show that in a second here. Now, another property of waves is that if you pass something that has a wave-like shape through a narrow opening, or around a corner or something like that, it causes the wave to sort of bend. And so you get what's called a diffraction of the wave when you pass it through a narrow opening. And so I have a visual of this that I found online. It's not very good, unfortunately, but it'll do. This is the diffraction of waves in a water trough. Is this set up correctly? It is, okay. And I'm going to just try and pause liberally to see if I can get it to show what I want. All right, so this is my narrow opening right here. Here are my waves that are propagating in this direction. And the opening is not narrow enough to really cause the diffraction, but you can kind of see it at the edges. So this is my opening. We're going to narrow it. Now you can really see the diffraction. So you do need a particularly narrow opening for waves passing through a narrow opening to start diffracting and curving. So you can see the diffraction going on here. Now, if you put two of these openings next to each other, your waves start to overlap. And you can see that in some spots where they cross over, you see something, but in others where they cross over, you don't see anything at all because they have canceled out. So, like the top peaks of the wave, because this is water going up and down, if the top of one wave met up with the bottom of another wave at the same time, the top part of the wave would fill in that gap, and you'd end up with nothing. And the overall water at that specific point in space would be flat or level or 0. And so if we look at that in a visual sense, that would look something like, oops, didn't click on the right thing. That would look something like this. So if my waves pass through an object with two slits in it, at some point along this barrier where I've just arbitrarily set a wall, for example, if this was water, at some part my waves would line up in just the right wavelength so that this wave coming this way and this wave coming from here would be off by lambda over 2. And the result would be that I would have a dead space at that coordinate. Now with light, there's a very easy way to measure this. We'll take photographic film and just put it right here. And whatever hits the film represents the state of the wave at that point. And you would get something that looks like this over here. This is called a diffraction pattern. Now, what's the takeaway here? What do we care about for all this? Because this is physics. This sounds like, what do we care about what this has to do with anything? Well, we just care about the end result here. If you are able to take something and pass it through two slits and then put an object behind it that can measure its result, and you get a repeating array that looks like this, what you have passed through the slits was a wave. So only waves produce diffraction patterns. And so if you observe a diffraction pattern, what you passed through here was a wave. Can you guess where we're going with this? You can do it with light. You can do it with water. Let's do it with electrons. So that's what we're going to do. If an electron behaves like a wave, we should see a diffraction pattern. If it behaves like a particle, then we should see kind of what we saw in the first part of the video, where the slit wasn't very wide, so the water just kept going through in a straight line. Particles would just hit the barrier and then stop, whereas if they cleared the barrier, they would just keep going and hit the detector in one spot. Oops. Spoiler, this is what happens. This is what you would expect to happen. This is what you actually see. This experiment was done in the 1920s, and nobody could explain it. So electrons are particles. Oops, dropped my pen. Because they have mass. We can measure their mass. We did that with the Millikan oil drop experiment. But this is not what we observe. We do not observe our particles just careening straight through and hitting only two spots on our film. When you fire electrons through a two-slit region, you get a diffraction pattern. And so what that suggests is that... Oh, gonna cough just a second. I didn't hit mute. I coughed and then muted my stream. What this suggests is that electrons behave like waves as well as particles. Now, it turns out that everything has a wave associated with it, but in this example that I'm going to do, and you don't have to do this calculation because I just promised you that we're not going to do any more calculations. The wavelength of an object depends on these things. So this is Planck's constant, which we have seen it already. Guess what this v is? It's not frequency, it's velocity. Because why not, right? Let's just confuse everybody and introduce velocity in an equation where we've been talking about frequency. And so what we're going to show, or I'm going to show in this example, and you're not going to have to do this calculation again, is that for a very small object, like an electron, the wavelength ends up being on the order of the wavelength of things like light. But the wavelength of a macroscale object, like a softball, ends up being so tiny that no known particle has a wavelength that small. And so this is called the Broglie wavelength. And it's basically just, if something is moving at a given velocity, it will have a wavelength associated with its particle, or particles. All right, so I'm going to work through this example just so you can see it. All right. Let's suppose that I have an electron moving this fast. So this is my velocity of my electron. I need to look up the mass of an electron, but I think it's this. Again, really stupid that I know this. Like, who gives a shit, right? Mass of electron. 9.109 times 10 to the minus 31. Wow, 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 wow. Kilograms. And you'll notice that I'm leaving in kilograms for a specific reason. And then we have Planck, which, who cares? So the Broglie wavelength is Planck's constant over mass times velocity. Is that right? I never remember this formula. Yeah, okay. There was the answer. Oops, that's okay. Uh, 2.65 times 10 to the 6 meters seconds inverse. All right. I'm writing it like that for a specific reason. And you'll see that in a second. Remember that if I have the inverse of a unit, I could just put it in the other spot. So this is now going to go up here. And I'm going to move that up there. And then what I'm going to do is I'm going to take my units, just these units. We're going to do a little bit of work with them real quick. All right. What is a joule? A joule is equal to 1 Newton meter, and a Newton is equal to a kilogram meter per second squared. So now I got to change my joules into what those units are. So this is going to be kilogram meter per second squared times meters for the Newton meter part. And you'll notice that, oh, look at this. Doot, 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 doot. Woo, that's the only unit that's left. So when I punch all this into my calculator, I will get lambda in meters. Hey, this is part of the reason why I'm not making you do this, because the units frickin' suck. But if I punch in all these numbers, negative 31 times 2.65 times 10 to the 6. I get this, 2.74, yeah, times 10 to the minus 10 meters. Or about 27.4 nanometers. Wait, am I going the wrong way? Hold on. Times 1e. Yeah, I went the wrong way with this decimal point. There you go. About 0.274 nanometers. Now, that is relatively close to the wavelength of a photon in the UV region, because the UV region goes all the way down to like, I want to say like 100 nanometers or lower would be like 100 or 10 or so. We're getting into the X-ray region around there. So electrons behave in terms of their physical properties much like X-rays do. But now let's suppose that I use a different example here. We're going to throw a baseball. I'm not throwing the baseball because I can't throw it at 11 meters a second. I'm a weakling. I'm not that weak, actually. Maybe right now I am, though. And so if I plug in all the numbers for this baseball, where's my cursor? There it is. So the mass is 150 grams, and we're throwing it at 11 meters per second. its wavelength would be 0.150 and 11 meters per second. And we could just trust that the units will work out, and we'll just get meters out when we're done. Because I just showed you that proof. We don't need to do it again. Divided by 0.150 times 11. And I get this. Oh, I only get one sig fig there, or two there. So a macroscale object has a wavelength that is so tiny that there's no known way to detect this. There's no photon out there that has a wavelength of 10 to the minus 34 meters that we are aware of. Or at least that I am aware of, I should say. That would have tremendous energy. And you can actually kind of correlate this with energy. One electron having an energy to propel it at like 1% of the speed of light up here, that's a lot of energy to get the electron to go that fast. But it is one electron. It's really light. Now, how much energy would you need to put in the same sort of particle to get it to move 11 meters a second if it weighed 150 grams? You would need orders upon orders of magnitudes more energy. And the resulting energy of a wave that would have such a tiny wavelength that it's essentially indiscernible. So macroscopic objects have wavelengths, at least theoretically, but we can't observe them because they're just too damn tiny. All right, so what's the takeaway? Why do we care about the Broglie wavelength? Honestly, I don't know. Whatever, right? It's cool. Things have wavelengths and all. I mean, practically speaking, the use of it would be that if you could take objects and calculate their wavelength, and that wavelength falls on the order of that of light, then you can use those objects as light. For instance, you may have heard of an electron tunneling microscope. And what it uses, it doesn't use light, it uses electrons. And when those electrons hit the detector, we can then parse that as information visually. And you get really high resolution images of stuff because the electrons are behaving like waves. They're behaving in the same manner as light would. All right. On the screen here, I have an experiment that is set up to try and figure out some properties of electrons. And the goal here is that if I fire my electrons through the double slits, one at a time, I should be able to detect which slit they pass through because they'll hit the laser, and the laser will diffract light, and I will see that. And what ends up happening when you do this experiment, because this experiment has also been done, is that when you pass the electron through the laser, you hit just these two spots on the wall, which does not suggest that it's behaving like a wave here. It's suggesting that it's behaving like a particle. If you turn the laser off, you get the wave diffraction pattern back again. And if your brain just broke, that's fine. That's the normal response to this. Like, wait, why would it do that? And the best answer that I can give you at the level that we're studying this is the following. When my electron is traveling through here, it might pass through either of these slits. We don't know the outcome, though, if we don't have something in the way to detect it. And since I don't know the outcome, I can't predict from the diffraction pattern that would show up where it came from. But when the electron passes through and hits this laser, then it hits the wall right here, and we see that. Oh, it went through the left slot. But the only reason that the laser influences the experiment after passing through this is because the laser is between the wall and the detector. And what ends up happening is that the laser here imparts energy into my electron. So here's my electron, and it's going this way. Then I give it some energy. After I've given it the energy from the laser, it is no longer the same electron that it was before. Its state has changed. How, you might ask? Well, it's going in a different direction, or it's going faster, or it's spinning in a different orientation. Something has changed about it because we gave it energy, right? The laser is not a zero energy device. It has lots of energy in it. And I have changed my electron so much that this and this are no longer the same thing. I've basically destroyed all of the information I know about the previous electron. I no longer know how fast it was going. I no longer know which direction it was moving. All I know is that from this point forward, it continued and hit the wall. But before that, I don't know, because that information's been lost. So I don't know where it came from anymore. So even though this experiment is designed to set up, oh, I'll just detect the electron and where it will hit, the experiment is fundamentally flawed because we have destroyed that information and therefore can't get anything out of that. And this is a very bizarre way to think of the world. This is why quantum mechanics is so strange. If you do an experiment about something, you only learn about it after the experiment was done. You can't really get any information about it beforehand because the tools that we are using are so high in magnitude of energy that they completely transform the object that we're looking at. It would be like if you are playing marbles with, like, I don't, like, you know when you play marbles with when you're kids, like you have those little tiny marbles and you throw them, you try and hit other marbles or whatever. The equivalent of this experiment would be, okay, I'm going to do that, but I'm going to use a planet as my marble. All right, here's my marble. All right, I'm going to use this to play. And what happens? You basically crush everything and it's no longer what it was before, right? That's more or less what's happening here, just exaggerated. Any experiment we do on electrons to learn about them changes the nature of the electrons. And so we can only really probe the information one piece at a time, and all the other information that we got about it will be lost. So if I'm searching for which slot did this pass through, I can no longer determine whether it's going to behave like a particle or a wave, because that's a different experiment. And all of the outcomes that I get will say, well, okay, I'm looking for a particle. I'm going to get a particle. So this is a consequence of quantum mechanics with the wave-particle duality of matter. Light does this, electrons do this. And we summarize this as what's called the uncertainty principle. The uncertainty principle at a very simplified level is basically this. If you do an experiment and you're looking for a property of an electron, pick one property. That's all you get to learn about. So, for example, an object might be moving, and it might have a direction. I could learn about which direction it's moving, or I can learn about how fast it's moving. but I can't do both at the same time, because if I try and do both, between measurements, the object has changed. So whenever you observe something for an electron, your ability to observe any other property at its current moment is destroyed. And you just get a random result. Now, in this case, what our properties are that we care about are going to be electron position and energy and things like that. Most of the time, we're going to care about how much energy an electron has, but in figuring out how much energy an electron has, we lose track of where it is. We can never find out where specifically an electron can be around an atom. And this made Einstein furious. This made Schrodinger furious. Like, they thought that this principle was stupid. And so this is where the idea of Schrodinger's cat comes from. So let's talk about Schrodinger's cat for a second. Because a lot of people misunderstand Schrodinger's cat. People think that this is just an allegory or an analogy to talk about how something is both alive and dead at the same time. And sort of yes, sort of no. But here is the experiment. So this is Schrodinger's cat. And the experiment is, I have a cat, and the cat is in the box. Here's my cat. Inside the box is poison. There is a radioactive poison in here. I don't know how to draw the radiation symbol. That's fine. That is connected to a sort of door that could swing open. That is connected to a circuit that when some event happens, there is a 50% chance of this triggering. So if the circuit triggers, the door opens, the cat is bombarded with radiation, and then the cat is dead. If the circuit doesn't trigger, the cat will be alive. But what Schrodinger said was that, okay, well, imagine this is the scenario. I'm going to put the cat in a box. And while it's in the box with this device, the cat is both alive and dead because we don't know the outcome. Maybe the device triggered and killed the cat, or maybe the device did not trigger and the cat is alive. But until we open the box to check on it, we don't know the outcome, and so both outcomes exist. And Schrodinger said, that is the stupidest thing I've ever heard. The cat is either alive or dead. Whether we open the box doesn't matter, right? And for macroscale objects, that is true. But for microscopic objects, such as electrons and other particles of that nature, that's not true. Electrons and protons and other tiny particles follow this sort of idea, where it is just a probability. You have this probability of finding it over here, and you have this probability of not finding it over here at any given time. And that's the best that you can do. Because when you do the experiment to try and find something, you're going to change all of its properties in such a way that, oh, you found it. And it's very bizarre to think about it in this way. So my advice for wrapping your head around quantum mechanics, and this is why everybody freaks out, because you really have to hear this from multiple people, read it in the textbook, think about it a long time, is to think of everything that is involving small particles, like electrons, protons, and stuff, as probability. I just realized, yeah, you have the radioactivity symbol right there. I should have just copied someone's work. That's okay. So thinking of everything as probability will help us understand how chemistry actually works. Because in a chemical reaction, I don't really need to know specifically where something is. Like, where are my electrons? I don't need to know their exact location. I just need an approximation. And if I know that they are going to be in that region 95% of the time, that's good enough for me. And so that's what we're going to do. We're going to take our electrons, which behave like waves, but we can treat them as particles and have an expectation that, okay, my electron will be in this area some percentage of the time. And so I can then predict the outcome of a reaction based on things like geometry, orbital electron density, etc. And those are terms that we haven't discussed yet, but those are applications of it. That's where we're going. This is the uncertainty principle in mathematics. I don't really give a shit about this formula. But what this is just saying is that if this is a variable and this is a second variable, the product of these cannot be smaller than this. This is the maximum precision I'm allowed based on how quantum mechanics works. If I know where my electron is really well, I lose all this information about how fast it was going. There's a joke out there that you'll probably hear scientists say, and it goes along the lines of a police officer pulled over Heisenberg, and the police officer asked, "Do you know how fast you were going?" And Heisenberg says, "No, but I know exactly where I am." I underlined the wrong terms there. Do you know how fast you were going? No, but I know exactly where I am. And then the police officer says, "Well, sir, you were going well over the speed limit." And then Heisenberg says, "Well, shit, now I'm lost. Thanks a lot. Now I have no idea where I am." It's a really stupid joke, but it makes sense if you understand quantum mechanics. Now, again, what is the takeaway here? I basically just talked to you for like 20, 25 minutes about random bullshit. It might as well have been, right? And the answer to that is, well, if our electron was a baseball, we would know where exactly it was on this curve at any given time t. And you could model that. But for an electron, you can't do that. And so what we instead do is we sort of just go like this. That's not what we do. Is my pen not working again? Yeah, my pen's not working again. Hold on. I only have 20 minutes left, but I might as well just fix this. The screen will go dark for a second while I boot this back up. Boop. Instead of having a path where electrons move, so you know how we would draw planets going around the sun, kind of like this? With electrons, it's different. This is the region in which we will find our electron. To some degree of certainty, so like 95% or whatever. And instead of calling this an orbit, which would be how, like, say, the Earth moves around the sun, if this was an electron going around an atom, we would call this an orbital. Okay? So an orbital is the shape of the electron cloud, or where you would be likely to find the electron. It will be somewhere in this orbital. Where exactly, we don't know. That's the best we can do. Thanks, Heisenberg. So what we're going to be doing from here on out when we talk about electrons is we're going to be referring to where they are in an atom as their orbitals. The orbital is just a region in space that corresponds with electron density. And when I say electron density, I just mean the electron is more likely to be here. Or the electrons that are present in these orbitals are more likely to be here. So that's where this terminology is going to come from. We're going to consider atomic orbitals as these regions that electrons live in, and our job is going to be to define them. We define atomic orbitals by using a sort of address system. You've already seen this number of the address, n. This is the energy level of the wave function. N is just going to dictate how big the orbital is, because the more energy it has, the further the electron will be away from the nucleus, and the bigger the orbital will be. And then we're going to define other terms that pin down that orbital to the electron. Now it says 3 numbers here. There are actually 4. Oh, sorry. I misread what I had written. So there are 3 numbers. These 3 numbers are the address of the electron. So these 3 will narrow us down to what orbital. And then this last number is specific for which electron in the orbital. Now, I only have 5 minutes left to really talk about this. I don't know if I want to go into more detail than just what we have covered so far, because I'm going to get like a third of the way through the topic and everybody will get confused when we resume. Let me just peek ahead real quick here. I absolutely don't want to do this in 5 minutes, so we're going to stop here. But what I will leave off with is that there's not really much to study from what we lectured on tonight, other than just maybe like a few terms. You should definitely know how to use the Rydberg equation for finding out the energy difference between electronic transitions. But as far as quantum mechanics is concerned, think of quantum mechanics more as just a philosophy rather than like a set of rules. And that philosophy is just, I have very limited information about electrons. What information I do have is going to be based on probability. And we're going to take those results and explore how electrons live in orbitals. What I can show you in these next few minutes, I'm just going to skip ahead really quickly. You can see that this is going to get ridiculous. This is what our orbitals are going to look like. So you've probably seen this before, just in passing. So you've heard of s orbitals that are spheres, and then p orbitals which look like this, and then d orbitals that look like that. So these shapes are just the results of the waves, and you probably are looking at these and thinking, wait a second, this looks almost kind of sort of like those wave diffraction things that I showed you in 2D, except this is just in 3D. And that's exactly where we're going with this, is that for electrons that have given energies, they form these probability distributions, these electron orbitals. And so these shapes are going to represent where electrons live in space around a nucleus, if the nucleus is, say, like right here at the origin. All right, so let me go back to where we were. We're going to do all of this discussion about quantum numbers and stuff next time. All right, what else do I want to say before we go as far as like administrivia here? You do have a lab due next week. However, Monday is a holiday. So there is no class on Monday. Monday is President's Day. I will be available on Discord, and I will be available over email. You can send me an email about anything you want to at any time, and I'll answer it whether it's a holiday or not. But we won't have a lecture, which means that if you have last-minute questions, those are going to have to wait till Tuesday. Try and ask them to me in the Discord if you can, or send me an email. But if you absolutely have questions about the lab, we can address some of it for like 10 or 15 minutes on Tuesday. What else did I want to say about the lab? I think that's pretty much it. The lab isn't very difficult, but it is new content. And it's going to be forever until we have quiz 3. So quiz 3 is going to be pushed off until like week 8, and then you're going to have quiz 3, and then quiz 4, and then quiz 5 all of a sudden. So just sort of the nature of how the class works. But make sure you're staying on top of the chapter 3 stuff. It gets weird, which is the part that we're in, and then it starts to sort of make more and more sense as we do this. So stick with it and don't panic. That's really all I can say about it. Other than that, have a wonderful weekend, and I will see you next Tuesday. Cheers, everybody.